Okay, so I want to start where we left off in class or finish some of the things we didn't get to. So example 12 says, suppose that the sound at a rock concert measures 124 decibels. A, use the formula L equals 10 log I over I sub 0 to find the intensity of sound I in watts per square meter. The variable L represents the loudness of sound in decibels, and I sub 0 equals 10 to the negative 12 watts per square meter. So we're going to use this equation right here and just fill in all the things we know, which really is just that it was 124 decibels. So that's L, 124 decibels is the loudness of the sound, and that is going to equal 10 log of I, which is what we're looking for, over I sub 0, which they say is 10 to the negative 12 power. So we can divide both sides by 10, which is going to give us 12.4 equals log of I over 10 to the negative 12. And then we can use the quotient rule for logs to rewrite the right side. So we'll have 12.4 equals log of I minus log of 10 to the negative 12. So log of 10 to the negative 12 is log base 10 of 10 to the negative 12. And that just means what exponent do you put on 10 to get 10 to the negative 12, and that's negative 12. Another way to think about it is if you use the power rule for logs, you can put that negative 12 in front of log of 10, and the log of 10 is just 10. I mean, it's just 1 because you're asking the question, what power do you put on 10 to get 10? And that is 1. So negative 12 is what this is going to equal. So 12.4 equals log I minus negative 12. And so you've got, this becomes plus 12, so you can subtract 12 on both sides, and you get 0.4 equals the log of I. And then you can change this to exponential notation. So the base is 10, so 10 raised to the power, which is 0.4, equals the number, which is I. So 10 to the 0.4 power, if you punch that into your calculator, is about 2.51, and that is in watts per square meter. Okay, and the next one says, if the threshold at which sound becomes painful is 1 watt per square meter, will the music at this concert be physically painful? And it says ignore the quality of the music. So that's supposed to be, I guess the book has a sense of humor sometimes. I don't know. But yes, it's going to be painful because it's at 2.51 watts per square meter. Okay, so here are just a couple of examples of equations that are models of, used in different disciplines. So you've got P equals 100e to the kx minus 100. So if we wanted to solve this equation for x, add 100 to both sides. We want to isolate the exponential term in this, so we'll add 100 to both sides. So 100e to the kx, and then we'll divide both sides by 100. So P plus 100 over 100 equals e to the kx. And then to get x by itself, we're going to have to take the natural log on both sides. So natural log of p plus 100 over 100 equals the natural log of e to the kx. Natural log of p plus 100 over 100 is equal to kx, natural log of e. Natural log of e is just 1, because what power do you put on e to get e? That is 1. So on the right side, we just have kx. And then to find out what x is, we can just divide both sides by k. So we would have 1 over k natural log of p plus 100 over 100. Okay, so part B, given L equals 8.8 plus 5.1 log of D, solve for D. Subtract 8.8 on both sides, and then we can divide by 5.1 on both sides. And then we can change this to exponential form. So we've got a common log on the right, so the base is 10. So 10 raised to the L minus 8.8 over 5.1 is equal to D, and that's what D is. Then we have exponential growth and decay. So let y be a variable changing exponentially with respect to t, time, and let y sub 0 represent the initial value of y when t equals 0. Then for a constant k, if k is greater than 0, then y equals y sub 0 e to the kt is a model for exponential growth. If k is less than 0, then y equals y sub 0 e to the kt is a model for exponential decay. So this kind of model is used for bacterial growth. It's used for decay, like in carbon-14 dating, things like that. So it's also can be used when you're talking about investment. It's similar to A equals P e to the RT, where P is your principal investment, and then R is your interest rate, and T is the amount of time it's been invested. And this is with continuous compounding. Remember, we talked about this with Euler's number, and that's why Euler's number is important. So anyway, suppose that you have 15,000 invested, and at the end of 3 years, the value of the account is 19,356.92. Use the model A equals P e to the RT to determine the average rate of return under continuous compounding. So the rate of return is R, so you're trying to solve for R. So we have A equals P e to the RT. So our A is going to be 19,356.92. That's the amount that we have after 3 years. So we're going to put in 3 for T, and A will be 19,356.92. And then our P, our principal investment, is 15,000, and we're going to solve it for R. So we put in that big number for A and 15,000 for P, and 3 is our time. And so we can divide both sides by 15,000 to get the exponential part by itself. And then we will take the natural log on both sides. First we'll divide the big number by the other number and get 1.29. Then we'll take the natural log on both sides, 1.29, natural log of e to the 3r. And remember that the natural log of e is just 1, so 3r times 1 is what you would get on the right side. And so you'd have natural log of 1.29 equals 3 times r. If you divide both sides by 3, you're going to have natural log of 1.29 divided by 3, and that's going to be your interest rate. And if you punch that into your calculator, 1.29, take the natural log, divide by 3, and you're going to get an interest. R is going to be about 0.085, so that means your interest rate would be 8.5%. Okay, so this is example 3. It's the one we started in class, and we'll just go ahead and start at the beginning. So this says on January 1st, 2010, the population of California was approximately 37.3 million. On January 1st, 2019, the population was 40 million. Let t equal 0 represent the year 2010. And so we want to write a model for this particular situation that looks like P of t equals P sub 0 e to the kt, where t is the number of years since 2010, and P sub 0 is the population in 2010 because that's where our experiment begins. So that's P sub 0. And so they tell us that in 2019, the population is 40 million, and we can use this to figure out what K is, because K is the special constant that goes with this particular situation. So we'll start out by finding K. So P sub 0, P sub t, we're looking at P sub 9, because 9 years after 2010 is 2019, and that's the information they've given us, is equal to P sub 0. P sub 0 is the population in 2010, so that's 37.3, and then e to the kt, and in this case, t is 9, so 9k. And we know that the population in 2019 is 40 million, so that should equal 40 million, but we're just writing our equation, and so our answers will be in millions. All right, so now to find out what k is, first of all, we're going to divide both sides by 37.3. So we'll have e to the 9k equals 40 over 37.3. So natural log of e to the 9k is equal to the natural log of 40 over 37.3. And therefore, 9k times the natural log of e is equal to the natural log of 40 over 37.3, and divide both sides by 9, and natural log of e is 1 because what you put on e to get e, and that power is 1, so that's 1 9 times 1 is just 9k times 1 is just 9k. So we'll divide both sides by 9, and we'll have k equals natural log of 40 over 37.3 over 9. And if we punch that into the calculator, 0.0078. And you want to go to at least 4 decimal places on k, because it's going to really change a lot if it's not specific. All right, so we know what k is, and now we can write our model for this particular situation. So the model would be P of t is equal to P sub 0, which for this particular experiment is always going to be 37.3, because that's the population in 2010. That's our beginning year. And then that will be E to the 0.0078 t, because we've got our k now. So that's the model that we can use for this particular experiment. So the next part says use the function from part A to predict the population in 2025, round to 1 decimal place. All right, so now we're going to find P of 15, because remember, we have to count the years from 2010. So we're looking at P of 15, and we'll see what we get for that. So P of 15 equals 37.3 E to the 0.0078 times the time, which is 15. And so to do that, we are going to use inverse natural log, because if you want to raise e to a power, you use inverse natural log. So we're going to hit 0.0078 times 15, and then we'll hit equals inverse natural log, and then we'll multiply that by 37.3, and that gives us about 41.9 for our answer. So it would be, our final answer would be 41.9 million for the population in 2025. All right, the next part says use the function from part A to determine the year for which the population of California will be twice that of the year 2010. All right, so now we're looking at the population in 2010 was 37.3 million. If we want to figure out when it will be twice that much, we will multiply 37.3 times 2, and that gives us 74.6, and that's what we want to get for our P of t. So we're looking now, in this particular problem, we're looking to figure out how many years it will take for this to happen. So we're going to be looking for t in this part. So 74.6, that's twice the amount, is going to equal 37.3, that's still P sub 0, E to the 0.0078 t. So time, when will this happen, is what we're looking for. So we're going to divide both sides by 37.3, which is going to give us 2, because 74.6 is twice that. So 2 equals e to the 0.0078 t. And since our unknown is in the exponent, we're going to need to take the natural log on both sides. So natural log of 2 is going to equal natural log of e to the 0.0078 t. And we can bring that exponent down. So that's 0.0078 t, natural log of e. And the natural log of e, as we said before, is just 1. So 0.0078 t times 1 is just 0.0078 t. So now we'll divide both sides by 0.0078, and that will give us t. If we punch that in, we'll hit 2 natural log and divide by 0.0078, and that will give us about 88.87 years until the population doubles. Okay, so we did talk about this in class. The U.S. population grew by 1.838.55% between April 2020, when the 2020 census was collected, and July 2022, according to recent Census Bureau estimates. This was the smallest two-year percentage increase in history. There have been just 431,000 more births than deaths since the 2020 census. So historically, like between 1950 and 2019, the smallest single-year excess of births over deaths was 923,000 between July 2018 and July 2019. So COVID played a central role in the minimal natural increase of modest population gain of the period. We based the model on a time between 2010 and 2019 before COVID really hit. So predicting about 2025 would not be as accurate as you would expect. So the model based on 2010 to 2019, the population was consistently going up. For the last year or two, it's been going down. Now, there are other issues besides COVID in this scenario. I mean, there are a lot of people moving away from California because of the fires and because of COVID, because a lot of people can work from home and they don't need to live near their workplace. So there are lots of reasons that the model is not accurate. And those are the kinds of things that if you are working as a person who does mathematical modeling, you have to take into consideration when you try to make predictions based on a mathematical model that it's based on some data that's not really the way things are now. So anyway, that's just gives you an idea of an application of this kind of math that is used in real life to, figure out all kinds of things on, sales for companies and population growth like this, which, you need to know to plan things like roads and schools and all kinds of things. So all of this is very much real life stuff that has to be done and figured out so that communities can function. Okay, let t and b be real numbers where b is greater than 0 and b is not 1. Then b to the t power is equivalent to e to the natural log of b times t. And we can quickly prove that this is true just by saying, okay, well, if is b to the t power equal to e to the natural log of b times t. So if we set those two things equal and we take the natural log on both sides, we're going to get natural log of b to the t equals natural log of e raised to the natural log of b times t. And so if we use the power rule to bring down those exponents, we'll have t times the natural log of b is equal to t times the natural log of b natural log of e. And so you can see that if we divide both sides by t natural log of b, we just get 1 equals the natural log of e, and that is a true statement. So they are equal. All right, so we're going to use that fact in this problem. So the population P of t of a culture of bacteria is given by P of t equals 5,000 times 2 to the t over 4. And so we can use this fact right here that b raised to the t power is equal to e raised to the natural log of b times t in order to write this rule for this function using base e instead of base 2 like we have it now. So we could write p of t is equal to, and we're looking at this, 5,000 times 2 to the t over 4. And instead of writing 2 to the t over 4, we're going to rewrite it like this as e raised to the natural log of the base, which is 2, times the exponent, which is t over 4. And so we could rewrite that as 5,000 e to the natural log of 2 over 4 times t. I'm just rewriting it. We'd have 5,000 e to the 0.17329 t. So find the population after 12 hours. So they want us to use both forms of the function in part A. So if we did it using P of t like it was to begin with, and we're saying 12 hours, so P of 12 would equal 5,000 times 2 raised to the 12 over 4 gives us 40,000. If we do it using the base e function, we would have P of 12 equals 5,000 e to the 0.17329 times 12. And if we punch that in the calculator, we get just about the same thing, slightly different because we estimated k, but it's basically the same thing. Okay, so we want to create a function q of t equals q sub 0 e to the negative kt. So to do that, we're going to have to figure out what k is. All they've told us is the half-life of carbon-14. The half-life, remember, is how many years it takes to have half of what you started with. Q of 5,730 is equal to Q sub 0 e to the negative k times 5,730. And that is going to equal that amount we know is going to be half what we started with. What did you start with? Q sub 0. So we can say that that equals Q sub 0 over 2. That is half the amount. Then if we divide both sides by Q sub 0, we can cancel those out, and we will end up with e raised to the 5,730, well, negative 5,730k equals 1/2. And now if we take the natural log on both sides, we'll have natural log of e to the negative 5,730k equals natural log of 1/2. And we can put that exponent in front, so we'll have negative 5,730k times the natural log of e equals the natural log of 1/2. Natural log of e is 1, so we can get rid of that. And we can divide both sides by negative 5,730, so we will get k equals, so the function is going to be q of t equals q sub 0 e to the negative kt, so negative 0.000121 t. All right, so an archaeologist uncovers human remains at an ancient Roman burial site and finds that 76.6% of the carbon-14 still remains in the bone. How old is the bone? All right, so we are going to use our function, and we're going to try to figure out what t is. We know that right now we have 76.6% of the carbon-14 there was in it originally. So that means 0.766 of the original amount is what we have. And that should equal Q sub 0 e to the 0.000121 t. Negative. And so the Q sub 0's cancel. And so we can take the natural log on both sides. So natural log of 0.766 equals the natural log of e to the negative 0.000121 t. And now we can put that exponent in front of the log. So natural log of 0.766 is equal to negative 0.000121 t, natural log of e. Natural log of e is 1, so that can go away. And then we can divide both sides by negative 0.000121, and so that is giving me about 2,203 years. So that is the age that that bone would be considered to have. 2,203 years is not that long ago, but when people try to use this kind of dating to figure out the age of very, very old things that are, that can be misleading possibly, because we don't know, a million years ago, if the Earth was here, how do we know that carbon-14 has always decayed at this rate? It's possible it decayed at a different rate. So there are all kinds of things people assume when they do these kinds of estimations of dating. So that's another thing to think about, and so that you don't have to always believe everything people tell you. And even science sometimes acts like they know things that they don't necessarily know for sure. Logistic growth models. The models we use for population growth don't take into account the fact that unlimited population growth is not possible due to limited resources. A growth model that addresses this problem is called logistic growth, which imposes a limiting value on the dependent variable. A logistic growth model is a function written in the form y equals c over 1 plus a e to the negative bt, where a, b, and c are positive constants. So this model imposes a limit on how high the population can get, because this term a, e to the negative bt, as t gets really big, as time gets really big, this term approaches 0, because e to the negative bt, that puts that in the denominator. So as t gets really big, e to the negative bt gets really, really close to 0. And so this term gets really close to 0, which makes the function become really close to c. But it will never actually get to c because that a e to the negative bt will actually never get to 0. And so you have this horizontal asymptote where y equals c. And so the graph will never get above that because that limiting factor there can never actually be 0. It's getting close to 0, but it can never be 0. So this limits the population growth. And so it gives us a better idea of how the population could increase up to a certain point. So the population of California, we're always talking about California for some reason. The population of California, P of t in millions, can be approximated by the logistic growth model. P of t equals 93.3 over 1 plus 1.5 e to the negative 0.013 t, where t is the number of years since the year 2010. Determine the population in the year 2010. 2010 is our year 0. That's the year we begin on, so we're going to be finding P of 0. And so we will just put in 0 for t into this function, and that means we're going to have e to the 0 power, which is just 1. So we can rewrite this with just 1 plus 1.5 in the denominator, and then when we divide that, we get about 37.3. So that means the population in the year 2010 is about 37.3 million, which is what we saw in that other problem. So we're going to use this function to determine the time required for the population of California to double from its value of 37.3 million in 2010, and then we're going to compare this result from example 3. So 74.6 is double 37.3. So we're going to fill that in, and then we need to find out what t is. And so we can multiply both sides by 1 plus 1.5 e to the negative 0.013 t, and divide both sides by 74.6. And then we can subtract 1 on both sides. And then we can divide both sides by 1.5. And then we can take the natural log on both sides. And then the exponent comes down in front. And then we can cancel out the natural log of e because it equals 1. And we will get t equals about 137.6 years. And if you remember back in example 3, it turned out to be 80-something years. So now it's giving a longer amount of time because of the limiting factors that this kind of logistic growth model puts on the population. It's going to take longer for it to double because of the way that this function estimates things like, resources available and that kind of thing. All right, part C, what is the limiting value of the population of California under this model? All right, so we talked about they've put in this limiting factor here that will keep the population from going over a certain amount, that horizontal asymptote. So as t approaches infinity, 1.5 e to the negative 0.013 t approaches 0 because this is a fraction where t is in the denominator because of the negative exponent. And so as t gets very big, that whole thing gets very small. And so the function is just going to approach 93.3 over 1, which is just 93.3. So the population wouldn't go over 93.3 million.